So stupid. Arr! Sound like a pirate. Welcome back to section K. This video is on K.2, which is relatively brief. This section covers approximating a series by truncating it. So just by chopping it off at a particular value. And then, all right, instead of looking at all infinite terms, because who's got that kind of time, we just look at the first, whatever, the first 12 terms. Okay, what's that equal to? Great, that's an estimate for the series. We will also consider in this section the error when we perform such an approximation. This is the first of 3 different methods of approximation that we're going to see in the option. This first one is we're only going to cover positive series in today's video. Later on in section K, we will see how to, K.3 actually, will cover alternating series. So that means when the sign is alternating from positive to negative. So we'll see how to estimate those. And then in section L, we'll deal with approximating a Taylor series. So here it is for positive terms. So let's say we have a sequence, and it's a series from 1 to infinity. And again, the 1 is totally arbitrary. That could be any number that we wanted it to be. So let's just say, for sake of argument, that this series does converge, and it converges to some value s. So in order to approximate the sum, we're going to truncate the series, and we will just calculate the sum from n equals 1 to n equals k. And we're going to call that s sub k. So this is the partial sum of the first k terms. Now on its own, this partial sum is not terribly interesting. I could easily grab a calculator and have it calculate a partial sum for me, or I could just add up a couple of terms. In practice, the problems we do are going to deal with a relatively low value for k anyway. What we're interested in here, however, is the error. And the error would be the difference between the actual sum and the kth partial sum. And we can denote this by r sub k. R, of course, stands for error, or as I like to pronounce it, err. And since that's the entire sum from 1 to infinity minus the partial sum from 1 to k, what's left over is the sum from k plus 1 to infinity. Now, as I said, we're dealing only with series with positive terms. And if that's the case, and we have a series that's going to converge, then I know it's got to be a positive and decreasing sequence of numbers. And we saw back in section I believe, that we could bound the improper integral from a particular value a to infinity. We could bound that in between or we could bind it, excuse me, grammar, in between the sum from a to infinity as an upper bound, and a sum from a plus 1 to infinity as a lower bound. So I will not re-justify that for you here. Again, you can jump back to section I if you'd like to see that. And we said that we could extend this as far as we want in both directions. What we're interested in here is actually going to be this section right there. In particular, this part. Right? Because this term here, I know I've used different letters here, which might be slightly confusing to you. I apologize. But this is in the exact same format as the error right here. And by the way, notice that the error for the kth partial sum is equal to the sum from k plus 1 to infinity. So it's always going to be one more than however many sums, however many terms we've used. And here, that error is less than or equal to the integral from, I wrote a here, but up here it'll be k, to infinity. So if I take 7 terms. So the error found between the sum, the total sum, and the 7th partial sum will be less than or equal to the integral from 7 to infinity. That's going to match. And that's the most important thing here. But remember, it only works when we have a positive decreasing sequence. Okay, there's 2 questions here, both related to the same series. So first of all, find an upper bound on the error using the 5th partial sum to estimate this series over here. Well, we just said that the 5th partial sum, the error, r sub 5, that's going to be equal to the sum from k equals 6 to infinity of 1 over k to the 5th. And that must be less than or equal to the integral from 5 to infinity of 1 over x to the 5th dx. So we're going to evaluate that integral. That's pretty easy to do. You're going to find that that's 1 over 4x to the 4th, evaluated from 5 to infinity. Putting in the infinity, we get 0. Putting in the 5, we're going to get positive 1 over 4 times 5 to the power of 4. That's a pretty small number. And that's our error is going to be less than that. And for the second question, how many terms of the series will we need to make that error be less than 10 to the negative 6? So less than 1 over 1 million. Well, we could guess and check, I guess. We could just keep on adding more terms, go one at a time until we find it, but I think it's going to be relatively inefficient. Instead, what we should notice is that in this answer that we just got, it was going to be 1 over 4 times something to the power of 4 every time, right? I mean, 1 over x to the 5th, that's kind of given to us by the series being 1 over k to the 5th. But this 5 right here, that came from that bound. And that bound came from the fact that we were using the 5th partial sum. So for the second question, really what we want to solve here is we want 1 over 4, whatever, n to the 4th, to be, then that's our error. We want our error to be less than, or less than or equal to, it's not going to matter, 1 over, missed a 0, 1 over a million. And so we're just going to solve this inequality. And you can grab a calculator to verify that you're going to have n is going to have to be greater than, you're going to get 22 point something out of this, so we need it to be at least 23 terms. And actually, I think I won't do another one because there's not really any tricks or curveballs that I could foresee here. I think it just, you're going to want some time to practice some of these on your own. You need to dedicate some mental energy into memorizing. You know, if you've got n terms, then we're dealing with our error is the sum from n plus 1 onward, and that's going to be less than or equal to the integral from n onward. So that's, again, not in the formula book, so you need to know that. But the rest of the math here is actually pretty straightforward. So yeah, we'll cut this one there. This can be a nice short video. In our next video, we will hit K.3, where we'll see some more tests for series convergence. But before you move on to that, you know, really take some time, make sure that you're comfortable with K.1 and K.2, because things are going to start to really snowball. The more tests we add, the more level of complexity that the problems can take on, and you'll have to really think harder about which tests are appropriate and which ones aren't, and you know, which method of calculating the error is appropriate given what type of series it is. So there's, you know, just things are going to start to compile. So I don't want you to rush through this. Really make sure you're comfy with what we've seen so far before jumping ahead.